we've got a problem up on the board here, and you'll see some problems similar to this in the homework. We're asked to complete a table of values. So here, this is a table of values for the function sine of pi over x. And then we're asked to guess the limit as x goes to 0 of sine of pi over x. Now, just looking at that, I can see that this is a function where 0 is not in the domain of the function. So there won't be a point on the graph whose x value is 0. But it's possible that as x gets close to 0, the y values are approaching some number. So we're being asked to investigate that. We're given this table of values where we've got a sequence of x values here that's to the left of 0 but getting closer to 0, and a sequence here that's to the right of 0 getting closer to 0. And we're just asked to evaluate the function and then look to see if there's a corresponding pattern in the y values. If it looks like these y values and these y values are approaching the same number, we'll guess that that's the limit. If there is no pattern, or if there are different patterns for the two sequences, we would guess that the limit doesn't exist. All right, now, when you're doing problems like this in the homework, where you're given a function and you're asked to complete a table of values, feel free to use a calculator. You are not allowed calculators on proctored exams and quizzes this semester, and so I strongly recommend that you do the majority of your homework without a calculator. That way you're practicing doing some calculations by hand so that that doesn't slow you down when you have to do it by hand on a proctored exam or quiz. However, use your discretion. Some problems would just be tedious to do by hand, even if my function was just the squaring function. If I'm plugging in a 3 or 4 digit decimal to that, that's just tedious. Feel free to use a calculator and feel free to round. On take-home quizzes, I can't keep you from using a calculator, but don't round, unless I tell you to. Okay. So, if I wanted to put a table of values on a proctored exam or quiz, I would either have to be very careful about what function I chose so that you could easily evaluate it without a calculator, or more likely, I'd do what we did in the last video. I'd give you a table of values that was already completed and just ask you to use it to guess the limit. All right, now it turns out with this function, we're actually going to be able to complete this table of values without a calculator. We'll have to review a little bit of trig as we do that, but this is trig that you should know. All right, now it's not obvious that we can do this, but let's take a look. If I try to plug in negative 0.1, so I'm getting sine of pi over negative 0.1. It's going to be easier to see what I want to do if I rewrite that decimal as a fraction. So I'm going to write this as sine of pi over negative 1/10. And I know that when I divide by a fraction, I just flip and multiply. So that would be sine of negative 10 pi. Now that I see that, it looks a little more reasonable that I should be able to evaluate that without a calculator. If I look at the unit circle, I want to remember that if I have some angle theta, the unit circle definitions of sine and cosine are that the x value of the point where this terminal ray passes through the unit circle is cosine theta, and the y value is sine of theta. Now, if I have a multiple of pi, any multiple of pi is going to put me either at this point or at this point. Now, this point would have coordinates 1, 0, because this is the unit circle, and this would be negative 1, 0. Either way, I can see my y value is 0. Notice my angle here is negative, so I'd be rotating clockwise. So here would be the angle of 0 would intersect the unit circle here, negative pi, negative 2 pi, negative 3 pi, negative 4 pi. I can pretty much see odd multiples of pi put me over here, even multiples of pi put me over here. Again, either way, I'm going to be getting 0 for my sine value. Okay, excellent. So if we do the next one, we're now looking at sine of pi over negative 0.01. Again, if I rewrite that as a fraction, that's sine of pi over negative 1/100th. That's sine of negative 100 pi. Any multiple of pi, sine is going to be 0. And so I'm going to stop writing this out. Dividing by negative 1/1000th is the same as multiplying by negative 1,000. This is going to be sine of negative 1,000 pi. It's going to be 0. Okay. Here, we're dividing by positive numbers, but this is dividing by 1/10, which is the same as multiplying by 10. Sine of 10 pi is 0. Dividing by 1/100th, multiply by 100, sine of 100 pi is 0. And this is also going to be 0. Excellent. So we filled in our table of values. And so now we're looking for a pattern. Do these y values and do these y values seem to be getting closer and closer to some number? Well, it seems like they're just always 0. Based on this, I would guess that this limit is equal to 0. That would be my guess. It's the best guess I can make based on this data. I think it's a good guess based on this data. It's also wrong. I like doing this example for a couple of reasons. One, we get to review a little bit of trig. Two, it points out the pitfalls of tables. I don't think we did anything wrong. We got the wrong answer, but we didn't do anything wrong. Tables only allow us to guess. And that means we're sometimes going to guess wrong, because tables don't capture all of the behavior. This is giving me 6 points on this graph. Let's see if we can figure out what went wrong. I'm going to think about the graph, because a graph gives me infinitely many points. And on a graph, I can get arbitrarily close to 0. Now I know what y equals sine x looks like, and I hope you do too. I'll just remind you, if trig is something that you're shaky on, that's something you're going to want to start brushing up on now. You can look at the appendix that's in the book on trig. You can also look at some of the supplemental resources that I've got posted on our Canvas site, and you can come to office hours and we can go over trig. Okay, y equals sine x looks like this. It's just, we often call it a sine wave. Now you'll notice there are infinitely many places where sine is 0. Okay. Now this is different from the function we're working with, which was y equals sine of pi over x. But we can sort of use our knowledge of this graph to figure out what this one should look like. The sine function is 0 anytime the input to sine is a multiple of pi. So this function will be 0 if pi over x is n times pi, where n is an integer. This fancy z here is just a way of saying the set of all integers. So this is saying n is in, or is an element of, the set of integers. Okay, well let's see if we can't then solve for x. So if pi over x is n times pi, I'm going to multiply both sides by x to get it out of the denominator. So pi would equal n times pi times x. Divide both sides by n pi, and x is 1 over n. So as long as x is the reciprocal of an integer, this function is going to be 0. Okay. Well, we were seeing that with our table of values, because we had 1/10 and negative 1/10 and 1/100th and negative 1/100th. And so these were all places where our function was 0. Let's just take a look. If n is 1, the reciprocal of 1 would be 1. So that's going to be a place where this function is 0. Now if n is 2, the reciprocal of 2 is 1/2. That's going to be a place where this function is 0. If n is 3, my reciprocal is 1/3. That's going to be a place where this is 0. And we'll have another 0 at 1/4, and a 5th, and a 6th, and a 7th, and an 8th. What's happening is the zeros, instead of being evenly spaced the way they are on the graph of sine, all of the zeros are sort of squished in this smaller interval. Now I'm going to have a similar thing on the negative side of the axis. So we'll have at -1, we'll have a 0. At -1/2, which is the reciprocal of the integer -2, we'll have a 0. At -1/3, and at -1/4. So I'm still going to have infinitely many places where the graph is 0, but instead of them being all spread out over the number line, they're all in between 1 and -1. Kind of crazy. So that's going to mean that there are infinitely many places as I get really, really close to 0 where my function is going to be 0, and our table of values just happened to hit 6 of those locations. But what's going to happen with this graph, you can see between consecutive zeros here, we're having a bump, either a positive bump or a negative bump. And that's going to happen here as well. The last bump here is going to just get elongated, so it never quite finishes. It never returns to 0. But then in between these consecutive zeros, my sine is oscillating still between a high value of 1 and a low value of -1. It's doing this same thing. It's just doing it with the size of the waves getting smaller and smaller and smaller. So it's oscillating like crazy. So if I graph it, it almost looks like it's just a solid graph. It's actually passing the vertical line test. It's just very, very steep because it's oscillating like mad in here. And then it ends up looking something like so. This should be all evened out. All the high points are at 1. Okay. So I could find a different sequence of points that was getting arbitrarily close to 0 where the y values were 1. Or another sequence of points where the y values were -1. Or any of the values that are in the range of sine. I can get arbitrarily close to 0 and find points that are taking on those values. So the table of values didn't capture this sort of crazy behavior that we have here, which is why the table of values was misleading. So I think it's important to take that as a word of caution. That's not to say that tables aren't a useful tool, but we shouldn't rely too heavily on them. We should also say, do I know anything about the behavior of my function that might cause me to be careful about trusting a table of values too much? And that's what happened here.